Hello, it's a joy to be here with you guys on this event hosted by Nalanda Bodhi. My thanks to Paulop Rinpoche, who I had the opportunity to meet here in Brazil. I hope you guys enjoy this material. I'm going to talk about quantum physics and trace some points or parallel or convergence that this theory has with Buddhism. I'm Eliane Xavier. I have a master's degree in quantum physics from the Federal University of Paraná, specialist in physics teaching from the Federal University of Rio de Janeiro, and I had my great insight regarding quantum physics and Buddhism when I started practicing Buddhism in 2004. So I even took this picture, then I made this joke. I put my book that I studied on university on the Buddha's hand because I started making this joke that the Buddha would have been the first quantum physicist because it's impressive how the universe that the Buddha describes this question of emptiness, the relation process and several other things that you're going to notice are really convergent with the world view brought by the quantum physics. So I'm going to quick tell you my story. I have a background in physics and mathematics, and I did my traditional academic career. And in fact, I've never imagined working with quantum physics in this way as I work today. But when I finished my master, I went to seek meditation for issues that most people seek for, which is anxiety, stress. I finished my master's degree very stressed and started to meditate, but I didn't even know that the meditation was within a context of Buddhist teachings. I found out later, but I really liked when I started to receive the teachings. I had a very strong connection with my master, with my Lama, and as I had just finished my master degree, everything was still very much alive in my mind. And as I received the teachings, things were connecting in my mind. And I was talking to my Lama, who was also a physicist. He had been already been a physicist in his life before he was ordained as a Lama, and he could confirm for me these insights that I was having, how really quantum physics it brings this view of the universe where even the teaching itself makes more sense. Because when we hear some questions, some points from the teaching with that view of a classical word, of a material word, of a solid word that exists independently of the observer, it becomes very difficult for us to absorb what is being introduced to us. Even the Lama Alan Wallace, he says that the quantum physics is like a preliminary study for the Dzogchen. So in a retreat, he was talking about that. Um, don't study Dzogchen at first. First, you need to study quantum physics, and then it will be easier for you to listen to the teachings later. So that's what I noticed, what I figured it out, that the quantum physics brings this worldview that is liberating, because the classical physics is something that gives us a very limited uh, where we are only the victims because the things happen and the universe is solid, separated from the observer. Me in my internal world is one thing, and then the external world is another thing. So we don't have too much options, and so we are victims. But this view that is liberating, it's finally in science. And great masters, Ared brought this vision as the Buddha brought, but only now, many centuries later, science itself is also reaching these results, which is wonderful and makes our path much easier, although there is resistance from some physicists in this language of science and spirituality. They think that these two has no relation at all, but many times these physicists are not specialized in quantum physics. Many physicists do not like quantum physics, do not like quantum mechanics. So the physicists many times have have master's degree, but many times they criticize quantum mechanics, but it's all a matter of paradigm. And I will talk about this further. Our universities still are in the paradigm of scientific materialism, so they cannot include consciousness in this science, but this is the only way out for the quantum physics to not become something paradoxical and non-comprehensive. So we're going to see today, I will show you guys how this developed. So why quantum physics connects with spirituality? Because the quantum theory show us a radical new worldview where the subtle phenomena of the universe now have a scientific description. So now they become part of the science because the quantum theory really jumped into the core of the matter. Like, what is the universe made of? What exists inside the atom? So, what did they find? It was a matter. They found vibration and energy that are things considered from a subtle or mystical word, but the science today need to work with it because the quantum physics brings mysterious phenomena, as you might have heard, that is called quantum entanglement. There are two entangled particles in a laboratory. Then these particles are separated in different labs. At any distance, they can be one particle can be close and the other one in another galaxy. And the moment that we change the measure of one particle, instantaneously the other one that are entangled also changed this measure. Einstein said that it was a is a ghostly action. Nothing can go faster than the speed of light. But this quantum entanglement is instantaneous. It shows that we have this non-local communication, which is communication beyond space-time. So this is a big paradigm shift because we thought that the space-time would be a background that all phenomena happen inside this bubble, space-time bubble. And quantum physics shows that no, there are deeper phenomena that space-time. Space-time itself is not something like finite, final, or ultimate as we imagine in classical physics. So quantum physics has been breaking these barriers, and physicists they do not know how to explain this because physics within the paradigm of scientific materialism materialism. The intention is to produce, to create technology, and they do not stop to look at philosophical question and what is behind the in these views. So I only found this on Buddhist practice where when all I studied started to make sense. So this started to create this impetus or motivation to teach quantum physics to the lay public because it's a complete transformation of looking at the world at ourselves too. Mainly quantum physics overthrows the idea of a universe separated from observer. Look how amazing this is. Niels Bohr brings this new quantum paradigm. Let's say that he defends it against some more conservative physicist. So, how about Einstein? This relativity theory, is it wrong? No, no, not at all. The speed of light still is the speed of light is still a limit for local phenomena that phenomena that happens within space-time. But modern physics has discovered a new range of phenomena which are not local phenomena, like non-local phenomena with instant communication. This can open a range where we can better understand the power of prayer, the power of our own motivation with our connection with everything. Because how does the universe knows whether when I do something with positive or negative motivation, right? Because we learn that the motivation that precedes any act is what will bring the energy, so to speak, of that act that will influence the whole where we are operating. And through non local quantum communication, these things become clearer, right? We can see better. So it's a new view of the world is very liberating. So we're starting from the very beginning, don't worry, because normally when we come to watch uh, a lecture of quantum physics, we have the feeling that we won't understand anything, but it's natural, don't worry. And the material starts for those who don't know anything. So we're going to get it right from the beginning of what is quantum physics. So quantum physics is a theory that started on the 20th century around 1900 to explain phenomena that were observed in laboratory but could not be explained by classical theory. So this is one thing that happens in science with a certain frequency that we have a theory, then we go to the lab and we make the experiment. And when we do the measurements in the lab, these measurements do not match with the measurements or the values found by the mathematical equations. So this is how the scientific method works. We have to have the theoretical model, which is a mathematical model. So we go there, we do the calculations, we arrive at the result, then we go to the lab, we set up the experiment itself and make the measurements. So these results must converge, right? So for example, one very single example, I'm studying speed, so I create an equation that relates space and speed. So if an object walks at a certain speed after 5 seconds, for example, it will be in a x space. Then I place the object to move around the lab. I take measurements. After 5 seconds, if this object it is on that space that I found with the calculations by the equations. So if yes, then the scientific model works. But if the result is different, then the model it doesn't work anymore. And this is what happened in the 1900 because at the turn of the century because there was an experiment done in the lab. It was called the black body radiation, where the values obtained in the lab were completely different from those calculated in the equations. I would not go uh, very into details because it's very technical. The only important thing to know is that this experiment is related with energy radiation, and we needed another way to understand energy because energy understood as a wave, the equations of classical physics were not able to reach the values that were obtained in the lab. So the quantum theory uh, arises modeling phenomena on a very small atomic, subatomic scales, but today it's believed that the word is quantum in all scales. This is important to talk to because the quantum physics starts on these very small scales because the quantum is a very tiny value, is a very tiny bundle of energy. But today it is believed that the word is quantum in all scales. There is the quantum biology. We use quantum physics to understand better photosynthesis, bird migration. So the quantum physics is really proving to be a theory that rules or controls the universe as a whole. So the Cartesian Newtonian paradigm is preventing us to opening up to new possibilities. Like we cannot anymore believe that the universe is static and exists independent from the observer. The Newtonian physics is a philosophy, is a determinist philosophy. And here's the second law of Newton's second law, F equals ma. And I want to draw attention to a point here. We're not speaking against classical physics. We're not stopping using it because even to send a rocket into space, we use the equations from classical physics. But it does, we cannot use this classical physics as a world view, as a paradigm to understand the universe. In this sense, it is very limited. So our point is this paradigm shift from the classical paradigm that believes in matter, that believes is in space-time as something defined, and among other things that I will show throughout our meeting here, and change to the quantum paradigm, which is a paradigm where all the teachings of the masters of spirituality make complete sense. So, some points for us to start this journey, some points of classical physics that quantum physics will turn down. Isaac Newton said that the atom would be a small particle, hard, like non divisible. Descartes saw the world divided between mind and matter. Laplace said that knowing the initial conditions, the future would be predictable. So there are just some points that guided classical theory. Now let's see how the quantum idea starts. These points we're going to review at the end, and we'll be able to compare how the quantum physics modifies those views of classical physics. Max Planck is known by the father of quantum physics because he's the father of the quantum. He was the physicist who proposed the idea of quantization. So there are people who come to me and say, "Oh, Eliane, I don't even know what quantization is. I don't even know what quantum physics means. I don't even understand the name." So we're going to start from scratch. As I told you, the quantum name comes from quantize. And what is quantize? Is divide into quantities, as the name suggests. So Max Planck, he proposed this idea of quantized energy. And it is very interesting because in the books it says that people asked him, where did you get this idea of quantizing energy? And he said it like in a kind of joking, it was an act of desperation because something absolutely new just appeared. This view of energy as a continuous wave did not explain what was observed in the black body experiment. So Max Planck proposed this idea. What if we consider energy as tiny packets of energy? Max Planck granulated the energy, so to speak. So in this figure, we have a ball that continuously descends a ramp. So here we call continuous movement because there is no break. There is no break in this movement. The ball is continuously descending at any instant of time. You can find this ball anywhere. On this side of the figure, we have a ball that goes down the stairs. What happens here is a broken movement because the ball will either be on one step on the other step. So there is a break in the movement. Here there is this little star that represents the break. It's not that the ball doesn't go here. It goes through here, but it won't stay here on the steps. It is an approximation to get the idea of what is quantize, what is to divide it into quantity. We have to remember that quantization is related to a break. So Max Planck in 1901 proposed the quantization of energy to explain black body radiation. So he took the energy that was not quantized, and he proposed this idea of quantization of dividing into quantities, dividing quantities into small pieces, and the energy started to be quantized in small packets that we call quantum. Here's the equation he proposed. As I explained in the scientific method, you have to have the lab and the theoretical part, which are the mathematical equations. So he proposed this very simple equation for the energy, the quantum energy. E is the quantum energy equals to h, which is Planck's constant, which is a very tiny value that he proposed, times this little Greek letter called me, which is the value of the energy. So here, uh, in a more explained way, Planck's equation for the quantum, E equals 8 me, where E is energy, h is the Planck constant, and ni is the frequency of the wave. Because remember, energy is considered a wave, so we take into account the frequency of this wave to to arrive at the quantum package. All right. So this is like the birth of quantum physics. So it was very successful because Niels Bohr, through these equations, physicists were able to explain exactly what they were observing. Through this Max Planck equation, they were able to develop the mathematical model and arrive to achieve at the results that they were getting in the lab. So that's wonderful. But a new theory for it really to have credibility, it needs to work several times, right? So the quantum physics really gets credibility in 1905 when Einstein uses this Planck model to explain the photoelectric effect, work for which he gets the Nobel Prize in 1921. So Einstein becomes very famous for the theory of relativity, but this Nobel Prize was for his work called photoelectric effect, where quantum physics really is born and gets and gains credibility because for the second time it explained this phenomenon that the classical physics could not explain. So the photoelectric effect is already a much simpler effect. So I'll explain to you here what happens. The photoelectric effect, it consists of throwing light on a metal plate. So for example, we start our experiment by throwing red light on a metal plate. And what happens? When the metal plate absorbs this red light, some electrons jump from the plate due to the energy that the plate received. When we put two lamps, in other words, we increase the intensity of the light, a larger number of electrons jump from the plate and they also change the color of the lamp. Instead of placing a red lamp, we placed a blue lamp, so the electrons jumped with a greater speed. And then, once again, classical physics did not even come close to explain this apparent, explain this experiment. Because here in the first situation, we increased the intensity of light. So instead of one lamp, we put two lamps. And with this, a greater number of electrons jumped here. There was no classic equation that could relate the intensity of light with the number of electrons. No equation could relate that. And also in the second situation, changing the light, the red light for blue light, the electrons jumped with a greater speed. So again, there was no equation that could explain that could relate the fact that changing the red light to a blue light, the electron would jump with a greater speed. So what Einstein proposed, he got the idea, Max Planck idea. He thought, okay, Max Planck proposed the idea that energy are packages, right? So he decided to apply this. He named every package Newton, and he proposed that let's think like this. Let's imagine red light as photons of red light, and let's imagine blue light as photons of blue light. So when we increase the light intensity, we are throwing more photons to the plate. Do you guys agree? So in that way, more electrons absorb these photons, and the electrons jump off the plate. Okay, so he explained the first part. So when I change the red light for the blue light, the electrons leave the plate with a greater speed. Why? Because the blue light photon carries more energy than the red light photons. Because remember the Max Planck equation, E, which is the energy equals h, that is Planck's constant, that multiplies me, which is this Greek letter, that means the wave frequency. So if the blue light has a higher frequency, look at this drawing here inside of the photo. So this photon will carry more energy. It's like a 10-cent coin and a $1 coin. Both are coins, but which one carries more energy? The $1, because $1 I can I can exchange it for a larger amount of things. It has more value, let's say. Uh, so the $1 coin carry more carries more energy. With $10, I can only buy one candy, right? And with the $1, I can buy 10 candies. So the blue light package carries more energy because the blue light has a higher frequency of vibration. That's what I showed you guys here. So remembering that the white light that we receive is made up of all colors at the same time. Maybe some people remember that in an experiment that we have in some schools, it calls Newton's disk, which is a disk with all the colors, the rainbow colors. And when this disk spins very fast, we see only the white color because it kind of shuffles everything and mixes all the colors, and we see only the white color. So the sunlight, the white light that we get, right? It actually is all these colors here, and the color that has the lowest frequency is red, and the one that has the highest frequency are blue and violet. So that's why we talk about ultraviolet, which is a frequency above the violet, and the infrared, which is the frequency below the red, which are already frequencies that our eyes does not capture, that we cannot see. Our eyes is like a calibrated instrument to perceive only these frequencies that go from red to violet. So here is like the embryo. Here they start like is being born. What we call in physics the duality of wave particle. That is the kind of the heart of quantum physics, because physicists thought in this way that light has always been understood as wave, but now we can also understand it as a particle. So things are already starting to get a little strange, a little weird, right? So Louis de Broglie will propose the opposite idea. He will say that what we think is a particle is not wave. So we're going to go through this on the today's class. So this part until here, it was to you guys understand like the birth of quantum physics. What does it mean to quantize? The meaning of word quantum physics and how the scientific method works, and the photoelectric effect that shows that is like the kickoff of this whole theory. Okay, so far so good. I hope so. So now we're going to see how quantum physics influenced atomic models. So here's a part that I think is very important. That is when we talk about scientific models, because this is something that is not clear, that professor teachers do not explain this in classroom, that science works with models. And now with atomic models, it will be easier for us to understand how this works. Okay, so what is a scientific model? A model is a way of explaining something to represent some phenomena of nature, phenomena that we are not quite sure how it is. Of course, because we always work with models, because we will never know how nature really is. So that's why models change over time. So in classical physics, the model of the atom came from antiquity, from the Greek atomists that imagined that the atom was the smallest piece of matter. The idea is very simple, very classic, and kind of in the common sense, right? So imagine that you take any object and break this object into smaller and smaller pieces until uh, there will be a time that we get to a piece that it wouldn't break anymore. So that was the initial idea of atom. So the word atom come from a Greek article that means indivisible. So Newton's classical model, he believed that the atom would be like a very marble toy, a very small ball, very dense, with a lot of matter that nothing could break, nothing could interfere in a way that it would change the composition of this marble toy, of this little ball placed by the hands of God Himself, so to speak, to build the universe, to build matter, right? But right in the beginning of the 20th century, a physicist named Thomson, doing experiments in a laboratory, he discovered a very tiny particle that all atoms have, which is the electron. So the atom is no longer the smallest part of matter. There is a smaller particle than the atom, which is the electron that it is inside the atom, right? So Thomson proposed this model that we called raising pudding model, because the electrons would be intermingled inside the atom, like raisins in a pudding. And about a year later, after this Thomson model, a scientist named Rutherford, who was Thomson's student, did some experiments in a laboratory using a very thin gold leaf. He took this very gold leaf and bombed alpha particles, which was a type of particle that they managed to isolate in the lab. They didn't even know what alpha particle were, but they managed to use to make some experiments, and these alpha particles pierced the gold leaf. So they threw alpha particles. There was a detector on the other side, and this detector registered that most of the alpha particles pierced went through the gold leaf. So Thomson thought if the atom if the atom was like the Thomson described, with the mass spread all over the atom, so the particles would not be able to pierce the gold leaf. And so that's how Rutherford discovered the atomic nucleus, because he realized that most particles crossed the gold leaf and only a very small number hit something apparently solid. So this model says that the mass of the atom is concentrated in the nucleus, and most part of the atom is what we call electrosphere. That would be an empty space where the electrons are there. So the proportion here is as if the atom were in the size of a football stadium, and the ball in the center would be the nucleus. So there's this empty space occupying like most of the atom. In 1913, Niels Bohr was the great architect of quantum theory. He used the idea of quantization to quantize the orbits of the electrons within the atom. So in the model before, the electrons are like scattered everywhere, but here no. Here the electrons are in defined orbits. They are quantized. Remember that quantization is like a break, right? So nucleus, it's still the same thing, and what changes is the distribution of the orbits of the electrons. So here's a larger figure. So here I have the nucleus, then I have a first orbit that I call K, the second orbit I called L, and the third one I called M. And these are the orbits where the electrons can be. So can an electron here be between one orbit and another? No, it can't, because either he is in one orbit or in another. The electron cannot be in the space between them. So it comes the very famous concept of quantum leap, because nowadays we talk a lot about the quantum leap, But the quantum leap happens when the electron changes from like jumps from one orbit to another. So imagine you have an electron on the L orbit, and it will jump, it will change to the M orbit. So we call this movement of one electron coming from one orbit and appearing in other orbit, we call this quantum leap. But this leap concept uh, is a rough approximation because when we leap, right, when we jump, we leave one place and we make a trajectory or a path. But in quantum physics, there is no trajectory, there is no path, right? In quantum physics, particles disappear from one place and appear in another depending on the energy and frequency that each orbit will have a specific energy and frequency. Each orbit will have a specific energy and frequency. The closer to the nucleus, the lower the energy, and lower the frequency too. The further away from the nucleus, the higher is the energy and the frequency. Then this electron here that will go from the L orbit to the M orbit, this electron needs to gain a little bit of energy to make the quantum leap because it's in an orbit with less energy. So for it to disappear from here and to appear in the other orbit, which has a greater energy and a greater frequency. So this electron needs to increase its energy and its frequency. Then it disappears from here and it's appeared there without ever passed through the space between them. So many people say that the quantum physics might be wrong, but there are some technologies that uses this concept in this experiment. The laser, for example, uses this concept and uses quantum physics. So it shows that this model uh, is right. It works. So our mind works in a quantic way. So, like the insight comes from a discontinuity. We don't know how the insight comes. It's like a quantum leap. Suddenly disappears from one orbit and appears in another orbit, like the electron that we saw with some other comprehension of the universe. So let me go back here to show you that the quantum leap can also uh, be in a reverse way. Uh, the electron comes from the higher energy orbit. He throw away the energy package and appears in another orbit with a lower energy and lower frequency. So this quantum leap model, we can have analogies with many complementary alternative treatments. We can make some analogy with consciousness levels, types of mind. So let me know later if there's something that you guys have an analogy with this quantum leap model. So here it shows the electron with some stars like a magic trick, like like a magic trick. It disappears from one orbit and appear in another. So the concept of quantum leap was conceived by Niels Bohr. According to Bohr, When the electrons jump from one orbit to another, they never cross the space between them. So this is the quantum world. So now let's see how we know the atom nowadays. The atom is made up of a very small nucleus and a cloud of electrons, that is the electrosphere. The nucleus is made of protons and neutrons. Until a few years ago, it was believed that the protons and neutrons were fundamental particles. And what are these fundamental particles? These are particles that do not break into smaller particles. But now we know that the protons and neutrons are made up of quarks. Proton is made up of three quarks, and the neutron is also made of three quarks. So quarks are the fundamental. But when we set up all this in percentage, but it was believed that the atom was full of matter, but it's not true. Only the nucleus is full of matter, kind of, so. But the nucleus has protons and neutrons. But the protons and neutrons are full of matter? Well, no, because inside of them there are three quarks. And every time we discover another particle inside of the first one, what is left? A lot of empty space. And when we put this in percentage, 19,999% of the volume of the atom is just empty space. So the matter is full of emptiness. This is a result that nobody expected. People thought that they were going to find matter existing, right? Because actually, this matter in the is actually full of empty space. What there really is energy and vibration. So now let's go to a very cool part of our subject. It's the observer aspect. You might have heard that in the quantum physics, the observer interferes in what is being observed. So to introduce this subject, I'll show you guys this cube. I want you to look very carefully and see if you're seeing one cube or two cubes. Pay close attention, take a good look at this figure. So we have this one cube, that is the front part, and this another square is the back part. This is the upper part, and this is the lateral part. But we also have this another cube that is from below to top. This square is the front part, the down part, lateral part, and this square is the back part. So I don't know if you can visualize these two cubes, but we have two cubes. So I will help you. So this is the first one, and then the another one would be this. Now, what are you seeing in this image? The cube is spinning, turning, but some people, as in the static image, some people would see one cube and another people will see another cube. In this image that is moving, some people will see cube turning to the right, and some people will see the cube turning to left, clockwise and counterclockwise. If you have someone at home, you can bring them now to see if they're seeing the cube turning clockwise or counterclockwise. So this is very curious when I teach this in a very big classroom. Some people see it turning clockwise, others see it turning counterclockwise, and sometimes the person is looking, and then it swifts, right? It shifts. Then you're seeing one thing, and then in another moment you're seeing another thing. So we start to realize that what I am seeing is not the same thing as the other person are seeing. So we do not see the same things at the same time. And you might have seen this on the internet. This dancer, it's a similar effect. You can look at the shadow on her foot, then it's easier to invert the how is it's spinning. Some people will see clockwise, some people will see counterclockwise. So now you might ask me why this happens, where the dancer is like really spinning. We want to know this truth, as if there was a truth independent from the observer. So as we see in Buddhism, there is a relative and absolute truth. So here in the relative level, the dancer, it will be spinning, it will be turning to the in a way that you are seeing. There's no absolute truth. This is relative truth. So like the blind faith that we have in our eyes is now kind of shaken because we see that the things are not the way we see. So take a closer look. Is there any difference between these images? Are they the same? Are they different? What do you guys think? If we remove the traces, the blue, white, and red, just the shadow part, are they the same? They are. But what makes us identify the shadow being the back part of the front is the way that we like build the image. Because when we see something, when our to our brain understand and make the image, we need to connect with something that we already have seen before, that we already know. So when we look to this shadow, but this is a unconscious process. We do not realize that our brain, our mind is like making up the back part of the shadow of the dancer. And my mind is like making up the front part of the dancer. Our mind make up things really fast. So I look and I see the back part of the dancer. I look and I see the front part of the dancer, and that's why we see different, turning clockwise, turning counterclockwise. So this is a very important point, that what we see is not free from our internal marks. So the quantum physics brings this question of, of how not exact, uh, of how our what we're seeing is not exactly how we think it is. So in 1923, de Broglie brings the idea of uh, wave of matter, the wave particle duality, and he proposed that we do the double double slit experiment with electrons. I'm going to take a screen with two slits and I'm going to throw electrons against the two slits. If we throw a marble toy, let's think if in the classic first. If I throw the toy marble, I'll get two marks. Two marks. So they went to the first, they went to the second. But if I throw waves, let's say water waves, I will get this figure number two. That it's a figure of interference. It's when wave phenomena are recorded passing through two slits. So when we throw electrons, what do you think it's going to show? It's going to appear. It's a fringe of wave interference or two marks. So first, let's understand how this experiment is done. So I have a source that emits balls or waves. So the balls go through the slit and make a mark. It can go through another slit and leave a mark there. When this source emits waves, the waves go through two slits and each slit becomes a new wave emitter. This is a property of the wave to bypass the obstacles. Now between the two slits, we have this what we call wave interference. Um, each point that the wave cross, we have a wave interference. Here's the constructive interference, and here's the destructive interference. If the value of one wave meets the value of another, it gives a constructive interference. If the valley of the one wave meets the peak of the other wave, we have a destructive interference. Right here, peak with peak, valley with valley, so constructive interference. And here, peak, valley, and destructive interference. And when we throw electrons against the two slits, the result was wave interference, as incredible as it may seem. So the duality of a wave particle is the great mystery of quantum physics, the one to which all others can be reduced. Then it turned out that the electron actually has the behavior of a wave, as de Broglie proposed, and he won the Nobel Prize a few years later. So the light that was a wave can also be understood as particle. The electron that was a particle can also be understood as wave. And now how the physicist will going to solve this? So now to make things even more strange, more weird, physicists try to observe which slit the electron passes through, that because it was very unexpected. They thought that okay, it might be causing interference fringes because the electrons might be, being thrown all at the same time, and they might be jumping over each other, and it's giving interference fringes. So they adjusted the electrons cannon to throw one electron each time. But even with that, the interference interference fringe pattern reappeared. So one electron is fired, is thrown. It splits, passes through the two slits at the same time, interferes with itself, and make the interference pattern on the second screen. So physicists were like, no, we're going to see how closer how that's is going on. So they put two slits to see which they would go through. And what happens? The electron uh, again started to behave like a particle. When we try to identify throwing a flashlight to the slits uh, to which the electron goes through, we can perceive their nature, their particle nature, that there are two slits, exactly what we expected, what electrons would do. Uh, being a baseball ball. So when we try to observe from which slit the electron goes through, he comes back to behave like a particle. So we question, the electron decided to behave differently because the electron knew that he was being observed. What is matter? Particles or waves? And waves of what? So it really like blows the mind, because if you don't have an open mind, you will like give up on understanding quantum physics. But it's here, a lot of technology is based on quantum physics. So how physicists came to a conclusion to this? So the electron is a wave of probability. And what does that mean? When the electron is thrown, when the electron is like released, it spreads like a probability wave, being everywhere at the same time until the moment of measurement or the observation. Okay, so for example, here the electron leaves here from the source, passes through a screen that has only one slit, and spreads out like a wave of probabilities, being everywhere at the same time. That is why we see the figure of interference. This is the interference wave. A, B, C, D detector. And these detectors will make a signal when the electron passes through. Then only one detector will beep. It's a beep. But you say, well, the electron is not like a scattered. So why doesn't all the four detectors beeps? Because when we observe the electron collapses, this wave of probability collapses. This collapsing is a term that physicists created. That means that the wave of probability has been destroyed, and we have only one defined, one final result. So here, for example, the detector D was the one who beeped, who made a sign. So let's go forward. When we look, we make the wave of electron start collapsing and places in just one place. Between our observations, though, electron spreads like a wave of possibilities in transcendent potentiality. So we look and it collapses. Not looking anymore, the electron spreads in wave of probabilities. So we look, it collapses. we can understand like that. So when we look, we collapse. I remember this was one of the first things that I connected Buddhism with quantum physics. It was the first subject between me and my Lama. And the conclusion is very interesting because as we already have this karmic structures as Simpsons had here, we already have our structure like beer, donuts, family time. So when what we get from the universe, what is the universe? The universe it doesn't exist outside, independent from the observer. The universe is a quantum field of waves of unlimited possibilities, but each one of us with our structure will collapse our reality in our world. And here in this curve is called a bell curve because it has this shape and it represents a quantum probability distribution. That means that this point is a higher probability point, but I also have this and this and this. It's a probability, it's a possibility with a less probability to happen, to occur. But if I always follow my patterns, my conditions, I kind of I'm closing this curve in my mind because it's getting more small, like very narrow. If I'm walking street and a person, bumps me, and I say bad words to that people. I always do that. So this might be my greatest probability. I always do that. And every time I repeat that, I'm like reinforcing this probability. So this probability increases. But let's say the person starts to meditate. I'm observing my impulses. I do not follow the impulses. I'm doing this, watching the mind. Maybe in a situation during the day, I might not be irritated if someone bumps me or someone irritates me. I'm not following this pattern. I'm kind of lowering, I'm opening this curve. So, meditation will help us to improve this bell curve. It will make us open up to more possibilities because we're not reinforcing this impulse to always respond in the same way. Does it make sense to you guys? And here, the point that I found very important to me, it was the idea of emptiness or shunyata, right? In the quantum physics, because the phenomena are not they are not defined. They are waves of possibilities, and we define in the moment that we relate to the phenomena. I will show you guys because on quantum physics books on universities, it is defined by the universe as a process of relationship. So nothing is defined. So that's why the phenomena are empty. But when we say empty, we associate with emptiness of classical physics, which is emptiness that has nothing. But in the concept of quantum vacuum is very different. The quantum vacuum is full of quantum fluctuations of particle, antiparticle, frequency, energy appearing, this annihilating, and the quantum vacuum is everything but is not empty. So the idea of emptiness is the idea is not the empty because there's nothing. It's empty because potentially it has everything, but it's nothing specific. Like the dancer. The dancer, she's turning to the right or to the left, clockwise or counterclockwise. She has these possibilities. Each one of us will look at it and will collapse in a way. So, is there something solid in the dancer? No. The dancer appears in my process of observation and with every phenomena. Like here, I have this glass of water, and then we can think this is a glass. But this is a glass of water only in my process. There is no like a atom glass, a glass of a atom of glass. It's a sum. It's a sum of possibilities. I can use it like to put some flour, to put a pencil as a pencil holder. An animal can give it a completely different use. So the infinite possibilities shows this emptiness aspect of phenomena, but why physicists could not observe the probability wave of the electron? Because our minds are conditioned to, so when we look at this wave of probabilities, immediately it collapses because the object and observers appear together. But what if the Buddha looks at this wave of probability? Will he collapses the wave? No. This, but this is me, taking my conclusions, because enlightened masters, his mind is already free. That's why in the teachings it says that the Buddha, when he looked at the person, he already saw the karma of the person. He can see all the infinity waves of possibilities. He does not collapses the person. So in the pure land of the Buddhas, let's say we could contemplate this wave of possibilities. But here, in our consciousness level, we will always collapse the wave in this movement of subject and object that arises together. Many there are many information here, right? So I have a few more, but we went through many things already. So I'm going to talk about the uncertainty principle. So physicist asks, what is the magic that of observers that turns waves of possibility into reality? So that's the big mystery. Physicists at the university, they call it the hard problem, because they have no idea how that happens. What is it? Is it the consciousness? Is this the environment? I mean, what it is? And they don't even like that. They don't like the question of to put like the observer, but they don't have any idea of what it is. So they call it the hard problem. And to create technology, it doesn't interfere. So they keep using the science in a very technical way. And they end up not taking advantage of the most beautiful part, the most transforming part, that is the world view, that the how can it change our mind and our understanding of the universe. So to wrap up, to finish here, I'm going to talk about the uncertainty principle by Heisenberg, where he says that the it was it came up experimentally when he went to do experiments involving quantum physics. Uh, involving a particle, they could not measure the value of the speed and the position at the same time. Either you measure the speed and don't get the position, or you get the position and don't don't measure the speed. I'm not going to explain this because you guys might be tired already. But the important thing to you guys know is that the very act of measurement interferes with the system. So there is no way to observe it without interference, without interfering. When I take a particle, when I try to measure the position, I already disturb the speed, and so we cannot see something that it is in an absolute truth in this world, because the very act of measuring, when I observe, I'm already like building up, I'm making up. So this shows the avidya. So why when we see one thing we don't see other thing? Because when I look, I collapse and I lose all the others possibilities. So Einstein, he was kind of and he said God doesn't play dice. He did not like this probabilistic aspect of quantum physics, and Niels Bohr said, "Do not tell God what to do." So Niels Bohr was a great like an architect of quantum theory to open that space. So this picture here with Niels Bohr, they had many conversations. Uh, so it's important to point out, to highlight that the physicists that were the are architects of quantum theory, they were kind of open to the of to mysticism. Niels Bohr got inspired by that Tao figure to compose the complementarity, uh, like Heisenberg felt connected with the universe, Richard Feynman. So when we're going to look at this great physicists, they had this openness to quantum physics, because quantum physics it like embraces the universe, and this scientific materialism that came after started to restrict quantum physics to a technique mathematic language, let's say. According to Einstein, the belief in an external world independent of the observer is the basis of all natural science, and the quantum theory changes everything. Quantum mechanics, however, faces the interactions between object and observer as the fundamental reality. Interaction between the object and the observer is what it is, the fundamental reality. It uses the language of physical processes and relations instead of qualities and properties, which are static. It rejects the useless notion that behind the universe of our perception is hidden the objective world, ruled by causality. Uh, Instead, it restricts the description of relationships between perceptions. So quantum physics defines the universe as relationship between perceptions. So as I promised, from classical physics to quantum physics. On classical physics, Isaac Newton said that the atom would be small solid particles, hard, indivisible. Quantum physics showed that matter is full of emptiness. Descartes shows that the mind and matter, the universe is divided between mind and matter. Quantum physics says that the observer is an active part in measurement. And Laplace said that knowing the initial conditions, the future would be predictable. So having a certain initial condition, I only have one possible outcome. Quantum physics, however, says about the Heisenberg uncertainty principle that says that if for an initial state, from an initial state, I have infinite possibilities to go. And Heisenberg says more that it's not that the quantum physics cannot determine the future. The thing is that the present moment is not defined according to the collapse that I make in the present moment. I'm going to have different futures. That's why the masters says bring your mind to the present moment, because in the present moment we have unlimited possibilities, because otherwise we will be like repeating our conditions like Simpsons, like Homer Simpson's figure that we saw, and we're not even choosing. We're just like following our bad behavior. So we have a primordial consciousness and a manifested phenomena. We have a light. So this consciousness that this light goes through the prisma of our conditioned mind, and it appears the phenomena, giving us the illusion of a reality of a solid world. So thank you very much. I'm looking forward to the questions. If you guys have any questions, so I have this book that I wrote. In English, it's called Primordial Quantum. It's not been translated yet. So I have part one where I explain the quantum physics, and the part two on the book that I relate to the quantum physics with the Buddhism. So I have this other book. It's called Quantum Key for young children. It's very it has a story, and in a few days I'll have my new book published. It's called the quantum, like quantum playing. It's for kids, and it was very nice to be here with you guys. Thank you very much. Thank you.